What's up, everyone? Day 2. About to go get my coffee. A lot of miscellaneous stuff to do today, like small things that need to get done, things like emails, just signing up for certain classes. I've been going to this new coffee shop, and the vanilla lattes have been better. I think I'm going to stick by this spot. It's a little further as a walk, but it's worth it. All right. We have our first unboxing of our YouTube channel. So this is a big momentous occasion. Hopefully this is the first of many unboxings on this YouTube channel. I know everyone's surprised, intrigued as to what this item could be. Let's take a look. I'll give you a clue. It's not that heavy. It's running shoes for a runner. Since my last shoes, their soles are basically ripped out. I wore them for a year. It's the same brand I always wear. On Cloud. This was a specific version for running. I'm going to show you what it looks like inside the box. It does look solid. The idea is that if it makes it easier on my legs, then I'm going to be able to run the marathon. Blind faith on these shoes to get me to the finish line. But yeah, this feels great, and I like the way it's curved. A little bit of curvature. I think it makes it easier to step when you're running. I'm going to wait on these until I actually do go for a run or go to the gym, which should hopefully be at some point today. Yeah, that's incredible.
Practices, and then we'll wrap it up with what's coming the last quarter.
Okay, coming back to the point I was discussing, wanting to be the best at something and taking action on it. Everyone owes it to themselves to aggressively get better. Give it absolutely everything you got. Exhaust every possible option. And if none of them work, then pivot and try something else that's as close to good as possible. I feel like a lot of people give up, myself included, to a certain degree. At a certain point, just stop trying. But I think everyone owes it to themselves to really try. Set the craziest goals and really work towards those goals and make it a reality. I was preparing for a TA role on AI. I thought the next portion of this video should be discussing everything about AI in around 5 to 10 minutes. I think everyone should be leveraging AI to their advantage in pursuit of becoming the best versions of themselves. You can ask it for anything from laying out an exact macro split to what you should be working on to get better. It has the answers to everything. There is no lack of information out in the world. It's just lack of people wanting to execute on those things. Every amount of money you get right now, you should be investing back in yourself to improve, become better, and make that money multiply. You are the multiplier, and you should be investing in yourself for learning to make that money multiply. Artificial intelligence can be deterministic or non-deterministic. Deterministic means you have a fully observable environment where you can see everything that you're supposed to see. Non-deterministic means there's a lot of probabilities involved in that environment. Assume you play a video game with a WASD key, but then every time you press W, only 80% of the time are you actually moving forward. That's an example of a non-deterministic environment where you're not guaranteed a specific outcome for making a certain action. That would mean, given any state you end up in, you should be able to adapt and get to the end goal. There are a few different key terms I want to break down in terms of what AI is. There are states, which are all the possible locations you can end up in. There are actions, which are all the possible moves you can take from said location. There's a transition function that models you moving from one state with one action, what the resulting state that you'd get to would be. And a reward function, which models a reward for any state that you end up in. Within deterministic, there is both uninformed and informed search. Think about a lot of AI as searching algorithms. You are essentially searching for a solution or a result or a prediction. And uninformed basically does that without any form of knowledge or guiding metric. Assume I don't have a map and I am in the middle of the forest. I need to figure my way out. I'm probably going to keep some rocks in certain locations to figure out where I was and try to find a way out. For uninformed search, we have a few algorithms that we use, like breadth first search, depth first search. These are two very notable algorithms. If you imagine a tree-like data structure,
covering breadth-wise every layer of nodes. You have a breadth first search, and a depth first is when you go to the deepest node first, and then branch back out, go into another layer, branch back out, and you're like, oh, we're done with this subtree. And then we branch out, and then we keep going. But the deepest part of every subbranch, a combination of both breadth first and depth first makes iterative deepening search, which now has the time complexity of BFS and the space complexity of DFS, the best of both worlds. DFS inherently isn't storing a lot of information. It's just storing that one layer's information or that one depth's information. Whereas BFS might, since it's using a queue data structure, might have to at one point store the entire last layer's data, which is B to the D, as opposed to just B times D for DFS. Next, we move on to informed search, and informed is where you have some kind of guiding metric to help you get to the goal. These are called heuristic functions. Heuristic meaning you have an idea of some way to measure how close you are to the goal. The most common ones are Euclidean distance or Manhattan distance. Let's go back to the grid example, but now we have a Euclidean distance metric to the goal. Generally, we'd want to take the path which shortens that Euclidean distance, right? So we want to move in the path. And assuming there's a wall in between and you can't just directly go down the diagonal to the goal, you're going to be taking steps which effectively reduce the Euclidean distance. So that's one heuristic that works. And a heuristic, which never overestimates for all nodes, is called an admissible heuristic. A few examples of informed search algorithms are the greedy best first search. Greedy algorithms are whenever you just go for the next best option for the immediate next move. And A star search, where for context, the A star algorithm is how Google Maps was made. All right. Now moving on to Markov decision processes and reinforcement learning. MDPs, like I mentioned, are for the other subset of problems that we discussed, non-deterministic, same set of states and same set of actions, transition function, and reward. We do this process called the value iteration algorithm, which finds two things for us. In any given state, what is the value of that state? How much is it worth? I'd assume a state right next to our goal in our map will be worth way more than if we're still at the start. If the goal is worth 10 points, a state right next to the goal might be worth 9.5 points, for instance. And the goal is to find the exact values of each of them. Next, we have our policy algorithm. Our policy is a set of on what to do from any given state. What is the best possible move to take from each state? Finding that policy algorithm is hard, expensive, and it takes multiple iterations. That's the purpose of using the value iteration algorithm to get both of these policy and values, and using that to effectively get from start state to goal state. So it's a fully observable environment, and you are making these decisions to get from start to goal. And the rational decision maker is trying to maximize their expected utility. Reinforcement learning, on the other hand, is a form of online planning. Take MDPs to be offline planning, where the transition functions and the rewards are given to us already. In online planning, we don't really know what those transitions or rewards are. Think about literally you as a child came into this world and you just figured it out by taking baby steps, by walking for the first time. A reinforcement learning algorithm does the same thing, where it's just moving in random directions, making inferences about the world and the reward it is getting and improving based off that. So just creating its own transition and reward and policy function based off its understanding of exploring the world. There's a big concept of exploration versus exploitation. Exploration being that you're going out and doing it, and exploitation meaning taking the best possible action with the knowledge that you know. So it's a balance of first initially exploring a lot and then exploiting a lot once you have that knowledge. Very similar to how human beings operate. There's passive and active reinforcement learning. Passive is more so when the objective of that is to find that transition and policy function to base your prediction off of. And active is more so just go out and do it. Go out and be you. Last but not least, I'll talk about both neural networks and natural language processing. Neural networks are built on the foundation of what is called a perceptron. A perceptron is basically, think of a neuron in your brain, but the artificial intelligence equivalent of it. It takes in a value and it spits out a value. Now, this perceptron can have a bunch of building blocks on top of it, specifically one called an activation function. Certain weights are useful to us and certain weights are not useful to us when making a prediction. Activation can scale it to a range of 0 or 1 to infer whether or not that data is useful to us. So this is called a sigmoid function, and the goal of the sigmoid is to use notably in logistic regression, is to elucidate whether this value is useful or not. And then the softmax function, which is applied on the outermost layer, basically gives us a set of probabilities of all the possible outputs and how likely we are to have one particular output. You imagine this is incredibly useful in the domain of natural language processing, where the objective of any NLP model is to predict what next word would appear in the sentence given a set of words. Assuming I say the dog, the likely next word is going to be barks. And the goal of the softmax is to be able to predict that with a high probability. Last but not least, I want to talk about game and adversarial search. This is a specific type of search problem. Talking about game and adversarial search, we have two-player zero-sum games where both players are rational. We have a player max who's trying to maximize their score and a player min who's trying to minimize max's score. So effectively, you can think about a chess evaluation bar, which kind of skews up and down based off how many pieces you have on the board and what your net score is. One player would be trying to maximize that, and one player would be trying to minimize that to infer that black is winning as opposed to white. The algorithms we use for this are the minimax algorithm, where we basically draw a tree of decisions where each layer represents a decision for max or min. And we take turns in a turn base where one layer is max, one layer is min. Then we can backtrack from the end of the game to find the best decision for max at any given point. To add on top of this, there's also the expect-Emax algorithm, where we're no longer dealing with entirely value-based decisions, but more probabilistic decisions, where there is an 80% chance min can do that or that. And still finding the net best move for max in that situation is what the expect-Emax does. Alpha-beta pruning is a cool concept which allows you to delete branches that we know for sure are not going to be useful. A very simple example would be assuming min has seen the value of 2 so far, and in the right side branch it has seen 1 so far, and we're still going to evaluate the remaining right side sub branches. There's no point in doing that because we know min by default is going to pick 1 or less, and we already have a 2 guaranteed on the left side branch. We'd rather just go with whatever values on the left side branch. So effectively that way we're pruning a part of the tree that we do not need at all. Hopefully this helped build some intuition on the entire concept of artificial intelligence. This was basically a grad school class's worth of content explained in around 15 minutes. And the objective was to take some of these ideas of AI and either apply it or find some kind of relevance for it in your own life. I would like to turn my life into a game solved by the minimax algorithm, where I'm the max and I'm optimizing to play better and do more things. But that's besides the point. I wanted to explain AI so I could put out a piece of content for today, and hopefully you're going to be seeing more miscellaneous content, things that are not entirely specific to a certain category, but are overall in the direction of the vision I'm trying to take with the growth of this YouTube channel. Hopefully you're able to take something away from it. See you guys tomorrow. Peace.